I don't think I can hear me. Can you hear me?
Yes.
Okay. So hello everyone. I'm Dr. Indranil Banik at the University of St Andrews, and I would like to explain about the theory known as Milgromian dynamics or MOND. This is based on a recent review, an invited review I've done for the journal Symmetry, which a little screenshot in there. Now, in this talk, I'm going to explain about various different kinds of evidence and what they might be telling us about MOND, or whether it might be right. So things like the radial acceleration relation in galaxies, but also things like the Bullard cluster, which are sometimes argued to be a bit of a challenge for MOND. So the first thing to understand is that if we look at the rotation speeds of galaxies as a function of distance from their center, so the rotation curve, that sort of looks like these Eulerian sort of decline. That's based on applying Newtonian gravity to the distribution of visible mass. So basically, just like planets that are further away from the sun in the solar system orbit slower, similarly, we would expect the stars and gas further away from a galaxy to be orbiting it slower, following approximately 1/square root of our decline. Now, the fact that this does not happen is related to, well, that's it's not clear why there is. This is dark matter, as in if you add a vast amount of around a galaxy, of a form that no one's ever discussed, it would perhaps explain the observations. So in this picture, galaxies look kind of like this. So you have the visible disk of a galaxy, which is rotating too quickly. And then you have like a halo of dark matter, which is shown in here. But what you have to understand is that there is no for this halo. So there's no direct evidence for the halo. What you actually have, galaxies actually wait, there's some problem with the transitions. Yes. Hello. Okay, I'm going to try seeing if this works a bit better now. The problem is all the slides are just. All right, maybe this will work, but I don't really expect it to. All right, so yeah, what I was saying is there's no direct evidence for this halo. What you actually have, galaxies look sort of like this, which is to say there may or may not be invisible mass up there. All you have is that the disk of the galaxy is rotating too fast. Now, one way to show the discrepancy is to show the rotation curve in a different way. In other words, you can show the centripetal acceleration inferred from the rotation curve as a function of the Gn, which is the Newtonian gravity you expect from the baryons alone. Now, the line of equality is here, and that corresponds to the Newtonian expectation for the rotation curve using just the visible mass. The point of the flat rotation curve problem is the actual G, the G obs, which is like the circular velocity squared divided by the radius, is much higher. So that's the discrepancy, but there is a very tight radial acceleration relation. So you can see that the data from 153 different galaxies, almost 2,700 data points, fall along this very narrow track. Yeah, and the big results are shown there, and the residuals are fairly tight. So that's the radial acceleration relation. One aspect to understand about it is the GN is very low here compared to the solar system, whereas typically, it's many orders of magnitude higher. For example, right now it would be about 10 to the plus 1 meters per second squared. And that's one thing. Now, that was rotationally supported galaxies, but if you look at elliptical galaxies, they often have like a halo of hot gas around them. You can use the X-ray emission from that to constrain like the temperature and density profile, and use hydrostatic equilibrium, completely independent of any gravity theory, to work out what the gravity is, and you can also work out the GN, or the Newtonian gravity of the baryons alone, and again you get a very tight relation. In this case, it's shown by these colored dots. The relation for spirals is shown as the blue shading in the background, but you can see there's a very nice agreement. And this applies from, I think, S0 galaxies. They sometimes have a disk of gas, which is subdominant in terms of the mass, but it is amenable to a traditional rotation curve analysis, like the 21 centimeter line. Okay, so that's the RAR in both spiral and elliptical galaxies. Now, one other thing I wanted to mention before explaining about MOND is the distribution of satellite galaxies around the Milky Way and Andromeda. So the satellites of the Milky Way line a thin plane, which is more or less at right angles to the disk. So the disk is horizontal in this view. And this is not a selection effect, only these regions are kind of obscured by the galactic disk of the sky. The ones above are moving in a sort of away from the viewer, if you like, in this view, and the ones below are moving towards you. But remember, that's how it would look for a distant observer. Inside the Milky Way, you can actually see the proper motions. You can see the satellites actually orbiting within this plane. The 3D velocity vectors are aligned. Around Andromeda, it's a satellite. There's also a satellite galaxy plane viewed almost edge on. The ones above are moving away from us. The ones below are moving towards us. There's proper motions for a couple of them. I think these two. So one of the most plausible explanations for how that happened is that some kind of galaxy interaction pulled gas out of the disk of the Milky Way into like a cloud of tidal debris, but it wouldn't be like a spherical cloud. It would be like a thin, dense tidal tail, which would then condense into tidal dwarf galaxies. So this process has been observed in external galaxies, so what I'm saying is basically the scenario would look something like this. So there's another galaxy has sort of pulled material out, and I think it's hidden behind there right at the moment. So if this gas later condensed into tidal dwarfs, you would get something looking like the satellite plane, the kind of thing we've seen around the antennae, the seashell galaxy. The alternatives to that scenario are not at all very likely. So just to give you an idea of how difficult it is to explain the satellite planes as primordial galaxies, basically the likelihood is about 1 in 2500 for the Milky Way and also for Andromeda. So what's shown in these plots is the aspect ratio, or the axis ratio of the satellite galaxy distribution in lambda-CDM cosmological simulations, run several thousand Milky Way analogs. And here is like the concentration of orbital poles. There is also like an additional factor, which is that the preferred orbital pole is aligned with the normal to the plane preferred by the satellites. And this too is hard to replicate, but that hasn't been included as a constraint. So we just look at matching the aspect ratio and the concentration of orbital poles within the tendency for the actual orbits to be in the same plane. There's the green star is the observed point. So yeah, it's about a 1 in 2500 likelihood for both the Milky Way and Andromeda. There's also something similar around Centaurus A. So here maybe the likelihood is 1 in 500, mainly because the data isn't so great, I think. But yeah, this was pointed out in a Nature Astronomy sort of comment piece of in like late last year. So The satellite planes are extremely hard to understand in lambda CDM. I'll explain a little more as to why exactly that is. Basically, you can get a plane of satellites out of this tidal dwarf scenario, but if you think back to the image I was showing, the tidal tails will only contain baryons, because to form such a thin, dense tidal tail, you need dissipation, and the dark matter is dark, so it can't dissipate. So you have baryonic tidal tails, baryonic tidal dwarf galaxies, and that's all fine, but it would mean that the satellites of the Milky Way and Andromeda in the satellite planes have very little self-gravity. As a result of that, they should have very little, very low internal velocity dispersions. But observationally, this is not the case. They actually have very high internal velocity dispersions, which implies that they must have rather strong self-gravity. Otherwise, they would have they would have sort of exploded now. They could not have remained bound. So the consequence of all this is that the internal dynamics of the satellite galaxies in the local group satellite planes can't be explained by Newtonian gravity, because to do that, they would need to be primordial dark matter-rich galaxies, and many, many papers over the last 15, almost 20 years have shown that there is no way to explain the anisotropy in both position and velocity space around the Milky Way and Andromeda, but also around Centaurus A. And these are the only three galaxies where we know the distribution of satellites well enough in 3D to actually know if they are in a plane or not. So this is an extremely serious problem for lambda CDM. This brings me on to Milgromian dynamics, which would explain the satellite plane issue fairly naturally, because then you could have the tidal dwarf scenario, but the elevated velocity dispersions are just explained as a consequence of MOND rather than of dark matter. So what exactly is MOND? That's something I'll explain a bit more on this slide. So basically, we have an empirical theory of gravity, which is Newtonian gravity, that was developed using solar system constraints mainly from before the invention of telescopes, like almost 400 years ago. If instead one uses the latest data on galaxies as a more secure empirical foundation for the gravity theory, then you would essentially arrive at MOND instead, which written as a Lagrangian kind of looks like this. So this is totally standard kinetic part, but the gravitational part is non-standard. If you apply the Euler-Lagrange principle, then you get this field equation. So one thing that I want to explain about that, just a sec, if this transitions. Okay.
Indranil?
Yeah, maybe this is a...
Yes. Can you start from slide number 15?
Yeah,
because
okay.
Yeah, good.
Right.
Of course, end of this slide, because we...
Yeah, no, I understand. So what I was saying is that because the tidal dwarf galaxies should have formed in purely baryonic tidal tails, tidal dwarf galaxies, I mean, they can and that's essentially and can't dissipatively settle in this. So you can have tidal dwarfs, but they would be purely baryonic. That would mean the satellite galaxies could be in a plane, but then they would have very low internal velocity dispersions, which is not correct observationally. They have high internal velocity dispersions. And that means that the internal dynamics of the satellite galaxies in these planes, gravity, as explained on this slide. I mean, some of these papers have shown that they can be explained naturally in MOND, which I'll come on to. So, of course, the idea in MOND is that you can have this tidal dwarf scenario. You can have purely baryonic galaxies, but all galaxies are purely baryonic anyway in this scenario. So the high velocity dispersions are then explained by MOND. So what is the idea of MOND? Basically, we have an empirical theory of gravity, the Newtonian gravity, which is not based on any quantum principle, but it's just empirical. And the main observations underpinning it are observations from before telescopes were invented about the motions of planets in the solar system. If instead we use, so that's from 400 years ago, if instead we use the latest data on galaxy scales as a more sort of reliable empirical foundation for our theory of gravity, we would come up with MOND, which is invented by Milgram in the early 1980s, to understand the rotation curves of galaxies without inventing large amounts of invisible mass, consisting of like completely undiscovered particles. So what happens in MOND is you have like a Lagrangian, which is sort of like this. There's a completely standard kinetic part, but the gravitational part is non-standard. Now, if you apply the Euler-Lagrange equation, you get standard equations of motion, but you get a non-standard gravitational field equation. Then what happens as a result of this, I was trying to share with you, is that in the regime of high accelerations, like in the solar system, where the Newtonian gravity is much stronger than A0, you just recover the standard behavior. But if the Newtonian gravity is much weaker than A0, then asymptotically you get that G equals square root of A0 Gn. Now, if you have the point mass in the center, then Gn would equal like the Gm over R squared. So you get a 1 over R force law, and that would lead to a flat rotation curve, because if you equate 1 over R force law with the V squared by R, is what would happen. That means you can explain the flat rotation curves in MOND. But there is another important aspect to this, which is that the rotation curve is predicted to be exactly this much. So MB is the mass of stars and gas. So now, if you try to then test that, the vast majority of which did not exist in 1983, by the way, then you baryonic mass against the flat line level of the rotation curve. The data points are sort of on here, and the MOND prediction is this dotted line. So it's worked extremely well across almost 5 orders of magnitude in baryonic mass. Now, another thing to understand about this is that in Newtonian gravity, if galaxies had substantial amounts of dark matter, if you put in like the usual cosmic fraction of baryons to dark matter, the galaxies would follow this dashed line, which is completely wrong. But the galaxies can lose baryons through that feedback processes, and then what would happen? They would kind of drop down this way. In other words, they would lose a lot of baryons, but because the kinematics, the forces are dominated by the dark halo, the rotation curve would not be much affected. So the feedback would, roughly speaking, take galaxies in the direction of the red arrow. The thing to understand there, though, is that the star-dominated galaxies, which are in dark blue, should have experienced like a different amount of feedback to these gas-dominated galaxies, which are in light blue. Therefore, it makes very little sense that both types of galaxies should be on the same Tally-Fisher relation. But there's also other things like the surface density of the galaxies, which vary hugely, and it doesn't affect at all where the galaxies are on the Tally-Fisher. So the other thing I want to mention was the lensing constraints. So, you get the same relation between the gravity experienced by non-relativistic particles and the light deflection is in general relativity. Also, we can get the gravitational waves to travel at the speed of light. So that's actually helped us in the MOND community, because it strained the types of relativistic extensions we're actually allowed. Now, just to show the weak lensing results, so this is what I mean by saying we have this general relativity-like relation between the deflection angle and the gravity felt by non-relativistic particles. This is just a totally standard. Also works on, but in MON, the G sourced by the same mass will be higher. Now, if you try to test the weak lensing, if you try to use weak lensing results of galaxies lensing background galaxies, you can infer the G from the deflection of background photons, which is probed by the distortions to background galaxy shapes. And you get the observed G, if you like, deduced from the deflection angle this way, and the Gn. So this is the line of equality. This is the blue region is the disk galaxy radial acceleration relation. So what should happen in MOND is it should kind of follow this line. It might be a little bit lower, depending on if the external field effect is important. Yeah, that's what should happen. Now, the actual weak lensing results come somewhere in this range, depending on exactly which survey you adopt. So we've managed to sort of confirm the MON prediction down to Gn of about 10 to the minus 15 meters per second squared, or 5 orders of magnitude below A0. It also works up to 1 order of magnitude above A0, and there isn't really much data on galaxies with much higher and of course, beyond that, we know in the solar system, Newtonian gravity works anyway, which is what MON reduces to. So that's the weak lensing. Now, another thing I wanted to get to is that if you try to fit rotation curves with dark matter, there is a great deal of flexibility which is not present in the MOND framework. So there was an experiment done in 1998 about fitting the rotation curve of a galaxy, where they had the rotation curve and they also had the image. So basically, they knew the amount of baryonic mass in the galaxy as a function of distance. Like from a color image, basically, and H1 data to tell you the amount of gas. Now, what happens in this case is that you actually cannot fit the rotation curve in MON. So the best fitting MON model is the solid black line here, which despite some modest changes one can make to try and improve the fit, is still really bad. So it wasn't possible to fit the data in MOND. In Newtonian gravity, however, Newtonian gravity obviously by itself doesn't work. You get something like some amplitude around here, which is completely wrong. But if you add dark matter, it's possible to actually obtain a very good fit. So it was possible to obtain like this solid line, which actually fits the data very well. But one thing to understand about this data is that it's not actually real. So the image shows a different galaxy to that used in the rotation curve. So in other words, the astronomers were able to fit this fake combination of photometry and kinematics pretty well in the dark matter theory, but not in MOND. MOND can fit real galaxies, but it can't fit like arbitrary data sets. Whereas in the standard model, you can, standard model of cosmology, I should say, the reason is that if you're allowed to add an arbitrary amount of invisible mass, it becomes possible to fit almost anything, including this completely fake data set. So that was the rotation curves. Now, one thing I want to mention briefly, because especially given the chair, is that it's also possible, recently it's become possible to detect the external field effect, which is caused by the nonlinearity of MOND. And basically, the idea is that if you have a system with even with a weak internal gravity, but there's a constant external gravitational field across the whole system, from like another galaxy from larger scale structure, then that weaken the internal gravity of your object and make it more Newtonian. So what that means is for a rotation curve of a galaxy, if it's isolated, the rotation curves should have flat outer rotation curves. which using these fairly isolated galaxies, that's deduced based on looking at the surroundings, it was found that the rotation curves are actually more or less flat in the outskirts, allowing for an arbitrary external field in the rotation curve fits. But bearing in mind it's an extra parameter, leads to this Bayesian information criteria being changed by less than 10, which indicates that there's no real preference for this extra parameter. One can fit these data with just the, assuming the galaxy is isolated. But when observers looked at galaxies which are in a region with a more significant external field as deduced from their surroundings, then they found actually very strong evidence for the external field effect. In particular, you can see on these panels that when they included the EFE, they were able to fit the outer parts very well, whereas without the EFE, they couldn't obtain such a good fit. The rotation curve is declining in the outskirt, and this cannot be explained if you just ignore the external field effect in MOND. So, and the change in the Bayesian information criterion is very significant. Now, similar results were obtained later, but also earlier by the chair, by Hossein Hagi in 2016, regarding this phenomenon, which is actually quite difficult to understand in the standard context. I mean, if you have a theory which predicts a breakdown of the strong equivalence principle and you observe exactly that, it becomes slightly hard to assume general relativity is still correct. Now, I don't want to talk too much about the issue of galaxy bars because you had a nice talk, I take it, by Taher yesterday on this issue. But basically, the galaxies often have a central bar, and this rotates at a certain pattern speed. But this rotation speed can be slowed down over sort of billions of years by dynamical friction from the halo. So you can see here in these different models, well, first of all, the red model is sort of the lambda CDM, and you can see there's a significant slowdown of the bar pattern speed over time. Let's call this omega p. In MOND, there isn't such a slowdown. Also, if you sort of artificially disable the friction from the halo, you get this orange line, which is kind of like lambda CDM, but without the dynamical friction. So it's not physically correct to do that. But it would lead to a flat behavior, as in the bar wouldn't slow down. Now, what I wanted to show here, is, okay, so I won't bore you with this thing as you had on this already. I just want to mention that in the lambda CDM, you get the R parameter is approximately here. That's the ratio of the bar length to the co-rotation radius. So that's in Eagle, but in TNG 100, TNG 50, it's around there. Observationally, it's these black contours. So there is like a very significant tension with lambda CDM. The observations rule out lambda CDM at well over 10 sigma significance. So that's the galaxy bar speed issue. Now, in the last part of my talk, I want to explain how we handle cosmology in MOND. So first of all, in the pie chart, if you like, of the universe, which you've probably seen before, looks like this. It looks very much like in lambda CDM. The only difference is instead of cold dark matter, we have hot dark matter. This would lead to the same overall mass energy budget. As far as the universe as a whole is concerned, that would create a standard background cosmology. You'd get standard like primordial light element abundances. MOND should be applied to the changes of the density from the cosmic mean. And there's also going to be, of course, the external field effect in MOND, which I briefly explained earlier. Now, what happens the cosmic background radiation is because you have a standard expansion history. This cosmic background radiation is at the same angular diameter distance as in lambda CDM. The important thing to understand is MOND is not very important then, because the gravitational fields are typically about 20 times A0. So not only is MOND unimportant, but the fact that you have sterile neutrinos instead of cold dark matter is also unimportant. The reason is CMB is kind of only sensitive to observations on fairly large scales compared to individual galaxies. And whether you have cold or dark matter, that tells you whether the dark matter is capable of clustering on galaxy scales or not. But we're not really observing galaxy scales when we look at the CMB. The Planck collaboration concluded that you need sterile neutrinos. If you have sterile neutrinos, their mass needs to be more than 10 eV by c squared to basically have a negligible impact on the power spectrum. So if you have like cold dark matter where it's like 1 billion eV by c squared, or you have hot dark matter where it's like 11 eV by c squared, it doesn't really make much difference as long as it's more than 10. But of course, that's what 11 is. So then you might be wondering, when does MOND actually even become important? And the answer is when the redshift drops below about 50, the expansion of the universe means that the gravitational fields become weaker, and then MOND becomes important. There's other evidence for these sterile neutrinos beyond the CMB. I should have said, in the CMB, with a rest energy of 11 eV, there would be the same amount of dark matter in the MOND picture as there is in the standard picture. So the height of the third peak is explained in just the same way as in lambda CDM. And the free streaming effects are not important at mass of 11 eV by c squared. Right. So
about 2-3 minutes.
Yeah, that's okay. So what I was going to say is there's other evidence for dark matter in terms, or at least for some collisionless matter from the bird cluster. You've probably seen that image before, but this actually can be fit very well with sterile neutrinos of a mass of only 2 eV by c squared, let alone 11. The dynamics of other galaxy clusters can be explained pretty well in MOND also. So I'll and get to the conclusions. Okay. Right. Okay, I guess that doesn't really work. All right, so I guess I'll have to go through this part whether I like it or not. So I've recently done a review on MOND, which you can see like the screenshot here, that's been accepted for publication in Symmetry. What I've done is I've compared lambda CDM and MOND with observations. I've considered like both how well each theory matches the observations and how much flexibility there was, the theoretical flexibility. So that ideally there wouldn't be any, because you'd have made a clear prior prediction or a priori prediction not informed by the data you're using to test the theory. And the idea is being, of course, that if you have an unphysical theory, I mean, how much flexibility you have directly tells you how well you agree with the observations. So basically, on this diagram, things would be along this diagonal. But a largely correct theory will be well above the diagonal. You can see there's a few tests like that for lambda CDM, but not very many. While for MOND, there's many tests above the diagonal, indicating that it's a much better theory. Also, there's no areas in significant tension with MOND that we identified, even though there's many falsifications of lambda CDM here. So when we tried to quantify this, what we did is we found the level of agreement with some particular test and subtracted the theoretical flexibility to come up with a score. So for MOND, it comes out much higher than lambda CDM in pretty much all the tests we considered. There is one test that you shouldn't consider for MOND, which is the high surface brightness galaxy rotation curves, because these were kind of used to set up MOND and to fix the A0 parameter. While for lambda CDM, the CMB anisotropies are generally used to set the free parameters of the lambda CDM model. So that's these open dots there. But as you can see, by now there's many types of evidence. So the loss of one line of evidence used in theory construction is not a major setback. So if we get the average scores then, for lambda CDM you get basically 0, while for MOND you get +2. 0 means the theory has basically little physical content. It's just how the amount of flexibility kind of directly tells you how well the model agrees with the data. While a score of +2 implies that you have a clear prior expectation which plausibly agrees, or you need a few auxiliary assumptions. These don't affect the results much, and the result is in excellent agreement with observations. So to summarize, lambda CDM has little physical content, especially in galaxies, it does agree with some observations, but that's because of the high amount of flexibility it has. So just to show you my conclusions then, in MOND we can explain the overall expansion history, the anisotropies in the cosmic background radiation, also evidence for like rapid growth of structure at high redshift, some of the very massive high redshift galaxies, including at redshift 13, a couple we found recently. We can explain the dynamics of galaxy clusters such as the Buller cluster and also virialized galaxy clusters, perhaps using the sterile neutrinos. But these don't affect the galaxy rotation curves, provided the sterile neutrinos are not too massive. There's many failures of lambda CDM on galaxy scales which MOND can explain pretty well, especially the planes of satellites with high internal velocity dispersions, for which there is no viable explanation in lambda CDM, despite many claims to the contrary. These have been rebutted. Other small scale failures, especially the high fraction of thin disk galaxies. So these two papers, the issue of Bow pattern speeds, the high velocity of NGC 3109, which was probably flung out from the Milky Way and Andromeda when they interacted with each other closely. So it's like a three-body process to the backsplash scenario. Then on larger scales, there's going to be some talks in the afternoon on this. That's what in this talk. Any questions?
Okay. Thank you, Indranil.
I am wondering about the result of MOND with testing dwarf spheroidal galaxies, velocity dispersion. As you may know, Angosh tried to explain this behavior of velocity dispersion of 8 dwarf spheroidal galaxies, but still some discrepancies do exist. What is your idea about testing these objects with MOND?
Well, I mean, dwarf spheroidals can be tested with MOND. In fact, like the chair's done a lot of work on this sort of issue. One problem is some of these often have very and inferring the velocity dispersion from these can be difficult, especially if some of these are interlopers. A lot of tests have been done. There was a recent detailed study by McGaw et al. 2021, which looked at the isolated dwarf galaxies, dwarf spheroidals in the local group, so not near the Milky Way or Andromeda. And these actually work very well in MOND. In general, like the better the quality of the data, the better the agreement with MOND. You have to bear in mind that if these had been near a larger galaxy, one might need to bear in mind the external field effect as well, and that can reduce the velocity dispersion, but not in an arbitrary way. This can be calculated quite accurately, like was done for the Dragonfly 2. There's also, regarding the low mass or the dwarf galaxies, one thing I wanted to mention is we've done a study on this AGC 114905, which was claimed to not work in MOND, but that's because they assume the inclination is 32 degrees from the elliptical shapes of the isotopes. But actually, it could be very close to face-on, and the observed ellipticity could just be a consequence of like intrinsic non-axis symmetry. So this galaxy is actually quite consistent with MOND once uncertainties are considered.
Okay. Any more questions? I have a short question. Yesterday after Tahir's talk, she showed that the bar speed from observation is inconsistent with N-body simulation results. And
yes.
In the conclusion, I think she showed that MOND can explain the bar speed. So is it based on N-body simulation or just what we expect from lower dynamic operation in MOND?
Right. So no, it's not. First of all, intuitively, it is true that because of the lack of dynamical friction, you would expect fast bars. But there are N-body simulations to show this as well. So you can see that this in this N-body simulation from Roshan et al. 2021a in MOND, you get this black region there. So it's kind of hidden here. That means that you expect the R parameter to be about 1 with a modest amount of intrinsic dispersion. That's based on an N-body simulation of a galaxy similar to the Milky Way or Andromeda. Observationally, it's like in this region. So yeah, it is not simply like an intuition, but also based on N-body simulations that have been published last year, that we would expect fast bars in MOND.
Okay, thank you very much.